So you have learned one of the most important theorems of linear models, namely the Gauss-Markov theorem. It's very pleasing in the sense that we put just the barest possible restriction on the parameter that we want to estimate, the linear parametric function that we wanted to estimate, and we got in a very constructive way the best linear unbiased estimate. So you might think that we have reached the holy grail of linear models, but no, there are problems. In order to arrive at that nice result, we have put a number of assumptions. If those assumptions are violated or nearly violated, then this optimality will be of no use for us, and in real life that is often the case. Take for example the situation, I take for example the assumption that all the sigma square have the same variance, they are all homoscedastic. In many practical situations we will find that they are either correlated or they are not homoscedastic. As I said, when I am measuring the length of something, if I make some of the measurements using a very precise instrument and some using less precise instrument, in that case you will not naturally be comfortable with taking the simple average. So if things violate, if the errors violate this assumption, or we have this situation that is not equal, then we need to generalize this concept, which is called generalized least squares. We will go into that later. So this is just to remind you that the Gauss-Markov theorem is not something like you just put everything blindly into it and whatever comes out of it you believe it blindly. Now here is another way by which things can go wrong. I am assuming that I am working with a situation where there are no outliers. Now every statistical method, when it is originally created, assumes that there are no bad observations. In practice there may be some outliers, that is quite possible. Now the least square estimators that we get generally are not robust. For example, even in case of measuring just a length, the least square estimator was the mean, and we know that mean is not robust. So if there are one or two outliers, some measurements that are quite far away from the rest of the measurements, those far away measurements will pull the mean towards it and completely ruin it. So if you suspect that there will be outliers, then you should use robust techniques, and robust estimators in general are not linear. So the fact that something is blue is not going to help you, because it is the best among unbiased linear estimators. It is not that it is best and linear and unbiased. It is best among unbiased linear things. So if there are nonlinear things, they might be better. So no one said that you should always focus your attention on linear things. Especially when you have outliers, nonlinear things might far outperform the linear estimators. A similar point is about unbiasedness. There are situations, in fact, very commonly occurring situations where you have what is called multicollinearity. Now, multicollinearity means that the columns of X have got some approximate dependence. Something like this: suppose you measure height of a person in inches and very stupidly also measure height of the same persons in centimeters. So because of some amount of numerical error, measurement error, these two things will not be exact multiple of each other, but very nearly 2.54 times one will be the other. So because it is very nearly, so they are independent but almost dependent. In that case, you will find that X transpose X is nearly singular. You understand, right? Because if if those two columns are exact multiples of each other, then the rank of X will be one less. Here it is not one less, but on the verge of being that. In such a case, you will find that allowing a little bit of bias is a much better idea than working with unbiased estimators. Unbiased estimators like least square estimators will have tremendously high variance. If you allow a little bit of bias, you can reduce the variance a lot. So the total bias variance thing will be better. What is called the mean squared error will be better. We shall see one such example later, the ridge regression. The point here is that do not blindly trust the Gauss-Markov theorem. It is correct, it's a mathematically proven theorem, but the assumptions that go inside them may be violated. In that case, the conclusion is also a great suspect.